Right, bit of a weird spot to film, but it's very windy outside, so we'll be doing it here for the time being. I've been thinking about boron a lot lately. I'd like to make some elemental boron, and the normal way that people go about doing this is to first make boron oxide and then reduce boron oxide at a high temperature reduction reaction using magnesium or another reactive metal like that in order to generate elemental boron. I was going to do it like that at some point, but then recently I've been looking for other ways to make it. In particular, ways to make boron that involve electrolysis. First of all, because electrolysis is kind of the theme of this channel, really. And second of all, because boron was originally isolated by Sir Humphry Davy by an electrolytic method. So it kind of seems like there should be some scalable electrolytic reaction that'll allow us to generate reasonable quantities of elemental boron. In looking online, I found one reference that said that electrolysis of a certain boron-containing compound would lead to the formation of elemental boron on the cathode. So this is a high temperature molten salt electrolysis reaction. So if this works, it'll fit nicely into our molten salt electrolysis series that we're currently working on. The reference states that elemental boron can actually be obtained by the electrolysis of molten borax or sodium tetraborate. Now, this is basically the only boron-containing chemical that is widely available. In fact, it's really widely available. It's available in most supermarkets as a washing powder kind of thing, I think. Anyway, I have some now, and we have the ability to do molten salt electrolysis. I have a furnace with the suitable power supply to do this kind of reaction, so I thought we might as well give it a go. Now, I don't know how likely this reaction is to work, because having just the one reference state that we can get elemental boron from electrolysis of molten borax isn't particularly convincing, but the starting material is so cheap, I think there's no reason not to try it. So, bit of a weird video we're going to get today, but hopefully we might actually see a small amount of elemental boron being produced. For the actual electrolysis, the reference calls for a graphite electrode as the anode. This will allow the anode to generate carbon dioxide by the oxidation of carbon. For the cathode, the mechanism is a little bit uncertain here. Boron in borax is part of the anion of the salt, so that's the tetraborate anion, and generally with electrolysis like this, the cathode can't directly react with the anion to reduce it. Instead, what we're probably going to do, according to this reference, is generate sodium metal on the cathode initially, and then instantly after the generation of the sodium metal, it will go on to reduce tetraborate ions to boron by a rather complex reaction. So we're really not expecting it to be an efficient process, but I'm thinking that if we melt down some sodium tetraborate using, I think, a stainless steel crucible as our reaction vessel and electrolyze it with a graphite anode and a steel cathode, we might be able to generate a small amount of elemental boron. I definitely think it's going to be a really weird video, and I don't think it's going to have a really high chance of success, but the melting point of borax when it's completely dehydrated is around 750 degrees Celsius, which is well within the capabilities of my setup. So let's head over and have a go at electrolyzing it. As the furnace slowly gets up to temperature, what's going to happen first is our borax in the crucible is going to dehydrate, so we should see a little bit of water vapor come off in the early stages. I think you can see that happening right now. Probably should have dehydrated it before trying to melt it, honestly, but can't change that now. Okay, that was a lot more difficult to melt than I thought it would be, but we are all connected and ready for electrolysis, so I will turn on the current and see what happens. That's 6 amps. As it turns out, I had to preheat the electrodes before starting electrolysis, because otherwise the borax would kind of start solidifying over the electrode surfaces. Hopefully though, now that we've got some current flowing, we might start to make some boron. I think I'll leave this going for an hour and we'll see how that goes. I'm thinking maybe the dark colour surrounding the cathode could be boron, but it could also just be metal oxides from the crucible or carbon dust from the anode. I'm not sure. Also note the flames that occasionally pop up around the cathode. I reckon that's small amounts of sodium vapour escaping and burning up in the air. Half an hour in, our electrolysis is still running smoothly. On closer inspection, I really don't think that the dark stuff on the outside there is actually boron. There's just way too much of it. When we're finished, I'm planning on just dissolving the contents of the cell in water. The borax will be soluble, but the boron, if we've made any, won't be. Things have been running for exactly an hour now. It's actually getting quite tricky to keep the borax molten, so I think I'm going to stop the reaction here. We were able to push 7 amps through the cell on average for that time, so we could have made nearly a gram of boron at 100% efficiency, so I suppose that's good enough. Anyway, we now have to move on to extracting it, if it is actually there, which I do doubt to some degree. Okay, I don't know what happened there, but that's why we wear PPE, I suppose. Now that everything's cooled down, we have the cathode, the anode, and the cell that we were using to electrolyze our borax in. First of all, the cathode, this has done pretty well. You can see there's a small glob of borax on it, probably contains a fair bit of boron that we made. I will process this along with the rest of the borax that we get to. The anode, you can see the end that was in the borax has dissolved away a little bit. If we compare that to how long a regular carbon electrode is, you can see we dissolved quite a bit of our carbon electrode. I'm hoping most of that has turned into carbon dioxide, but inevitably we're probably going to get some carbon contamination in our boron that we extract. So that's a bit disappointing, but there's nothing we can do about that. So that's just something that we have to deal with. Our crucible, you can see, did oxidize quite considerably. I mean, we had it up to close to 1,000 degrees for a whole hour. So, that's to be expected. It's done pretty well, and I'm pretty sure the borax has protected it to some degree. So that's okay. I'm sure we can probably use this again if we have to for another electrolytic extraction. But I don't know if there are any more that will require a small crucible like this. So maybe this is the last time you'll see it. The borax is still in here, of course. It's discolored considerably. But now that everything's cooled down, we can move on to the next step of our boron extraction, which is to just dissolve everything in some distilled water. Due to the fact that we have a solid mass of borax instead of borax powder, I have a feeling this is going to take a really long time. Now, after dissolving absolutely everything out of our crucible, which was a harder task than I thought it was going to be, borax is surprisingly insoluble in cold water, and even in boiling water, the rate of dissolution is really slow when you have a whole solid mass. So this took me a very long time, and as well, a whole lot of water to wash everything. But at the end of all that, and with washing our material multiple times with water, this is all of the stuff that was not soluble. As you can see, it looks pretty good, about what you'd expect boron to look like. So, maybe it's promising. But it's also possible that all of this material is just graphite and iron oxide. That's equally probable. But what we really want to do now is purify and test it. So the best way to purify it now, particularly to get rid of any metal or metal oxides from our electrodes or our crucible, is to wash it with concentrated hydrochloric acid. That won't react with the actual bromine, if we have any in here, whereas it will dissolve iron and iron oxide and any other metals that are present. It won't touch the graphite, sadly, so inevitably I think our boron product will likely have quite a bit of graphite or carbon contamination, but that is okay. Right now, this material weighs around 1.03 grams, so with our washing of concentrated hydrochloric acid, it'll be interesting to see how much mass is lost from our yield here. Oh, and by the way, our expected yield of boron, based on the amount of charge that we put through the cell, is approximately 0.8 to 0.9 grams. So, we might see that, but I doubt our process was 100% efficient. So, who knows? We'll see. Washing things with just a little bit of hydrochloric acid. Maybe a bit more. Some sort of reaction with something in there. See a small amount of gas generation. But what we'll do now is we'll wait and see whether that starts to clean everything up. After 2 washes of the material with boiling hot hydrochloric acid, this is what we're left with. This is 300 milligrams of material now, so we got rid of a whole bunch of it. If we actually have a look at the liquid we used to wash things with, it's really green, right? So that tells us that there's probably either iron or maybe even chromium in there. I'm hoping it's not too much chromium because that's a hassle to deal with in terms of waste. But we will deal with that later. This might be a reason to not use stainless steel in the future for this kind of process, because the chromium content, of course, poses an issue for the waste we generate. Our material itself, as I said, 300 milligrams of material. We don't have much left, and I'm starting to doubt that this is actually boron, because this material is very weakly magnetic, so it's attracted to a strong magnet, which tells me that it probably still has at least some degree of iron in there. At this stage, we just really want to know whether the stuff we have is boron or not. We have purified it to the greatest extent that we can possibly purify it. So to check our remaining material, the only test that I can think of for boron is a flame test. If we have elemental boron, doing a flame test on this stuff should reveal a very bright green flame. So I'm going to do that right now. If we see green, we know it's boron, or possibly, it could be boron oxide, but we're going to pretend like that's not true. If we see a green flame, we're going to say that this is boron. And yes, our flame test was a complete negative. So we have absolutely no boron in this sample here. All it is, I'm guessing, is finely divided graphite from the anode and maybe a little bit of some oxide of iron as an impurity. So a bit disappointing, but as I said at the start of the video, this was a little bit too good to be true, so I'm not too disappointed that this didn't work. It does kind of raise the question though, what reaction were we actually doing when we were electrolyzing the molten borax? And the answer to that is I've got no clue. So maybe one of you in the comments has a better idea than me about what was actually going on, but with that, I don't think there's much more to say about this reaction. As far as molten salt electrolysis goes, we've had a pretty good run. I mean, we successfully made aluminium, sodium, and lithium, so we're about due for one that doesn't work. And as it all turned out, I think the reaction still looked pretty cool. But with that, I'll end the video here, and hopefully our next video will work out a little bit better. See you later.